Okay, now the thing we want to understand in application to circular orbits. I'll try to draw a good circle at this point on the board, but it's not too bad. Look, bad perspective here, so don't expect miracles. Let's see what that looks like. Yeah, a little lopsided, but you get the idea. Okay. Okay, now in a circular orbit, or for any point moving at constant velocity, but circular orbits are certainly a case in point, you have velocities, and I used yellow for velocity, so I'll do it again here. Okay, so as you move around the circle, let's just say you move around maybe pi/6 radians, in intervals of pi/6 radians, but you can do any intervals you want. Okay, and you know everything's moving around this way. Can't see through my hand here, but I'll try to get a tangent. Okay, constant angular velocity. Your picture is going to look something like this. Not doing a great job here, but you get the idea. Tangent vectors, all of the same magnitude. Okay? So you have velocity vectors, tangent to the circle, all of, we're assuming constant omega, equal magnitude. One thing we can do with all these vectors is we can draw all these vectors with a common initial point. So the vectors, and make them a little longer, I don't have to keep the same scale. Start here at t equals 0, and then we'll have terminal points, and I'm drawing this the way I'm doing it because, well, I don't want to make a reasonably representative picture of what these vectors do. Okay, so okay, here we have the first vector, the second. So the vectors kind of go around the circle. These are the velocity vectors. They all have the same magnitude, even though I probably didn't do a good job of drawing them that way. Okay? They all have the same length. And there's an important consequence of that. So if I isolate two of the vectors, this one and this one, I can bring them out here. That's really a bad angle to draw it at, but we'll pretend that I did a good job of that. Okay? So it should be rotated out a little more, but you get the idea. Okay? Now they have the same length. The difference between this vector and this vector is we're going from this direction to this direction is just this vector. So I'm going to say this will be the velocity at some time t1, and this vector will be the velocity at some time t2. Now it should be clear that if I take this vector and add this vector, I get this vector. So we can say that v of t1 plus some vector equals v of t2. And I'll just put an underline here. Okay? So v of t1 plus whatever this vector is equals this. So that this vector equals v of t2 minus v of t1. Equals what I'll call delta v, the change in the vector from here to here. Okay, so now we can rewrite the picture. Where this is delta v equals v of t2 minus v of t1. Again, I'll label these just to be sure we understand. Okay, now this triangle is an isosceles triangle. Okay? So this is an isosceles triangle since velocity is constant. All these vectors have the same length, the same magnitude. So the length of this one equals the length of this one. So I'll use standard geometrical labeling and say we got this and we got this. They're identical in magnitude, which means that this angle and this angle have to be identical. Okay, well that's really important because what we want to know is what's the limiting value at, let's say, this point of the change in v divided by the change in t, because that's going to be the acceleration. So I can write over here, acceleration at a time t equals the limiting value as t approaches 0 of v of t, v of, we'll say t plus h, fairly standard notation, minus v of t. Okay? Well, this triangle is supposed to represent these two velocities. If we want the velocity at this point, then we're going to have to use triangles that are much closer. In other words, our v of t might be here, and our v of t plus h for small h might be here. Let's extend that a little bit so the tips are kind of in the right orientation. And again, we're going to have a delta v. Okay? And the acceleration is going to be approximately equal for small h acceleration at time t is approximately equal to the delta v over delta t. So we can just think of a tiny, very slim triangle with h approaching 0, so the triangle approaches just a straight line. The delta V approaches 0 in magnitude, but always has a direction that's pretty close to this one. Okay, well, we have this. And delta V makes an angle close to 90 degrees with V. Why is that? Simple geometric argument. This angle has to equal this angle. This angle is getting close to 0. The three angles have to add up to 180 degrees. So if this one's close to 0, these two have to add up to something close to 180 degrees. And they're the same, so they have to add up to something close to 90 degrees. Now, I'm just uttering that verbally. You should understand geometry well enough to understand that that's the case. Hey, I better write a little something down. Okay, so we'll call this angle here, I can't call it theta because that invokes the angular position here, but we'll call this angle alpha. So there's an angle alpha down there. Okay? Now, two angles, delta V with V of t plus h and with V of t are equal and add up to 180 degrees minus alpha. It's got a bad looking alpha, it's still bad looking, but we'll live with it. Incidentally, when I wrote this down, I wrote it carelessly. Not t that approaches 0, it's h that approaches 0, the difference between t and t plus h, the time interval, the delta t. And I didn't write this as delta t. I'll write that as delta v over h, and I probably should have written this as delta t in the first place, because that's really what h is. I hope it's probably a little confusing, sort through it, and at the end I'll replace that with the delta t. Okay, anyhow, these add up to 180 degrees minus alpha, and as h goes to 0, alpha goes to 0, so those angles approach 90 degrees, and it follows that A of t is perpendicular to V of t. Now remember, that's not a general thing. It's not a general statement. It only applies if omega is constant, but that's what we're talking about here. Okay? So for constant angular velocity, you have an acceleration that's perpendicular to the velocity. Therefore, back toward the center. And I can say, I think I can get it written in here, hopefully legibly. Therefore, centripetal. Okay? Now what does this have to do with orbital motion? Well, We'll take care of that next.